Okay, good afternoon, good evening, everybody. Welcome to today's SETI Live. My name is Simon Steele. I'm the Deputy Director of the Carl Sagan Center here at the SETI Institute in Mountain View, California. I'm joined today with three guests, Jim Davenport, University of Washington astronomer, Errol Grekovsky from the SETI Institute and a comet expert, and also a chief scientist with Unistellar. And we'll talk more about Unistellar in a bit. And Wael Farah, a radio astronomer at the SETI Institute, based up at the Institute's own radio telescope facility in Northern California. So, welcome. We are here to talk about an invader from outer space. Interestingly, this is the first adult science fiction book I ever read, Rendezvous with Rama, back in the 1970s, about a strange alien spacecraft that was detected by an asteroid detection system moving into the solar system. It was a great read. It still is a great read, but it was science fiction. And then in 2017, an object called Oumuamua swept into the solar system, the first interstellar object that moved through the solar system. We were then followed in 2019 by 2I Borisov, a comet that came in from interstellar space. And now there's a third one. They're coming in thick and fast at the moment. And this has just been detected. And we're going to talk about this object. It won't be the first talk we'll ever do, because this object is going to be observed and scrutinized in great detail. But we're going to talk a little bit about what it is, what it isn't, and how we can find out much more about it. Let us know where you're tuning in from. We'll call your names and your locations out. And of course, we're very happy to answer questions. Pop your questions into the chat. But we're going to start with Jim. Tell us, how was this thing discovered? What's going on here?
Yeah, so 3I Atlas, as we have lovingly named it, is, as you said, the third interstellar object. 3I, third interstellar. We're very clever with names this way. And what's great about it is, in my mind, is that it's been named after the telescope that discovered it, or the telescope system. This is the Atlas telescope system. This is actually a network of 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, I believe. And they sort of provide nearly a full sky mapping of the night sky almost every night, looking for moving objects mostly. They discover a lot of other things, supernova, flaring stars, all kinds of other fun stuff. But the big mission for them is to look for moving objects like asteroids. And at first, this was detected as just a little dot of light moving across the sky hour to hour, like so many asteroids are. I think Atlas has discovered more than 1,000 new asteroids in the last few years. This is very normal for them. What became very exciting was not just one. I mean, they're all special asteroids. We love them all. But what was very exciting was when we realized it was moving a little too fast based on where we thought it was. Night after night, it came back, and this object was moving too fast for something that would normally be bound to our solar system. And when we started to do orbit modeling of this at the Minor Planet Center especially, they found that it had what we'd call a sort of hyperbolic orbit, or something who did not look like it was in some kind of nice ellipse. You know, we all think about Kepler's laws and the ellipses that govern where things move in the solar system. This thing is not moving on an ellipse. It is moving on an arc, almost a line, as it is barreling through the solar system. And that sort of set off worldwide excitement amongst astronomers and everyone else.
Yeah. Now, ATLAS stands for Asteroid Terrestrial Impact Last Alert System, which sounds the most apocalyptic name and cool telescope name I've ever heard, which is wonderful. So it's looking for near-Earth asteroids. Obviously, they're worried about sort of early warning for impacts and everything. But this thing is still quite far away, and an Ariel that this was just a pixel in the sky, wasn't it? Moving. Do we know much more about it now as it sweeps into the solar system? How fast is this thing moving?
This thing is moving pretty fast. So its incoming velocity is faster than the other 2 previous interstellar objects. And so that's kind of a cool thing. It tells us this thing has a lot of energy, which means wherever it came from, it was ejected with a lot of energy. We do know a little bit more about it now that since discoveries this last week, we've learned a lot about it. Pretty quickly, we learned that it is cometary. So it's not just a little blip in the sky, it's a little fuzzy blip in the sky, which is very cool. We're seeing dust come off of this thing, form a coma and a tail. So it does also have a cometary designation in addition to its interstellar designation.
Okay. Everything in astronomy has at least 7 or 8 different names, doesn't it? Just to make things very, very confusing. Yep. So you're going to talk a little bit about the optical observations of this object. Now, of course, we're at the SETI Institute. We're interested in aliens and spacecraft. And so what's the first thing you should do when something comes in from interstellar space? You should observe it with a radio telescope. Well, what's going on from your angle?
Yeah, fortunately, we own a radio telescope, and we can pretty much operate it and point at any source of interest at the SETI Institute. And so we learned about the source on July 2nd. Pretty much, our team, our ATA team, which I would really highlight the incredible effort. I'm representing a team of researchers and researchers and engineers and students who worked on this project for the last 7 days, and just the amount of work that the team has done is pretty much incredible. Having said this, the object was detected, or we got to know about it on July 2nd. And we were pretty much on sky that night. We just waited, of course, for the Earth to rotate for us to be able to see it. And that was around 10 p.m. Local time. And the first thing we tried to do is to look for, or to observe the object, looking for narrowband signatures. The reason why we look for narrowband signatures, because these kind of signals are proxy for intelligent life. And so we currently have over 7 hours of data. That equates to 21 terabytes of data, which I think, if I am doing my math right, it's roughly 7,000 high-definition movies that we have on disk right now. And we're still assessing this data. We're just going through it as we speak. But yeah, hopefully you'll hear more the next few days.
Great. We'll talk more about the data reduction and what this means or doesn't mean. I'd like to welcome people who've tuned in. Joe from Tennessee. We've got David from Grand Prairie, Texas. Santiago, Chile. Louisiana. Carlo in Ireland. Sweden. Poole in Dorset. Hi. Toronto. Dublin, California. Maryland, New York City, and so on. So thank you, everybody, for tuning in and joining us today. Jim, this is early days for observations of this object. Can you just put it into context with the first 2 interstellar objects that we've discovered, and why are we suddenly being flooded with interstellar objects, or what's the situation?
So I think I have to responsibly say, I don't think they've just now started showing up. I think it's more that we've just now started noticing them. We've thought that this would probably be a thing we would detect for a long time. But these objects, they don't tend to come that close. Thankfully, we're not bombarded with these things coming from interstellar space. So probably at any given time, there could be dozens or even hundreds of these things in the sort of greater region of the solar system. Most of them are very small. They're very far away. And like asteroids don't really emit their own light. They only reflect sunlight. So a very small rock out by Saturn, out by Uranus, it's going to be very hard to see, very unlikely to see. What's gotten lucky about this is we are monitoring the sky, almost the entire sky, every single night with telescopes like Atlas, like the Zwicky Transient Facility, and very soon from Chile, this big monster, the Rubin Observatory, which I work a lot with. We are monitoring a huge amount of the sky, nearly the whole sky every night, to fainter and fainter depths. And as we have pushed that faintness limit down to the really small object class, where we can start to see things that are kilometers across, tens of kilometers across, we've started to pick up things that are more distant and small things that are passing through. And so I think that's what's made the real difference is missions like ZTF and Atlas finally getting enough depth and enough sky coverage. And of course, also having the computing resources to quickly go through this data every single night and look for things that change.
Yeah. So it's technology, really, that's discovering it. And these things are always been passing through.
That's right.
See them. The Oumuamua and Borisov, the first 2 were very different objects. Can you just give an overview and how that compares to Atlas as far as we know?
Yeah. Well, as Ariel said, the Atlas already shows indications of being a comet, even at something like 4 AU, so it's sort of out in the outskirts by Jupiter right now, even already showing cometary emission. So it has sort of a fuzzy tail sort of sticking out the back. That is very different. Oumuamua didn't show a real clear cometary tail, but it did have some cometary-like properties in its colors and its motions. And as far as I understand, Borisov looked like just a rock. And so this is already a little different. What we don't have a good handle on yet is the composition. Although what's great is, unlike the other two, we have more lead time. This thing will be coming in for the next few months. It'll pass behind the sun sometime in late this year, October, I think. And we'll be able to watch it in through early next year. And so we'll be able to get monitoring data, not just with ATA, but of course with ATA, but also every other ground-based telescope that we can, and space-based telescope, and get it coming in as it gets heated by the sun, and then get it, very excitingly, as it passes out, and we get a really clear view of that sort of cometary tail. And we'll have a really good sense, I think, of what this is made of, what kind of material comes flying out the backside.
Yeah. I know Oumuamua, I think, was discovered when it was heading on its way out, wasn't it? So it was.
Yeah, that's right. We didn't get a good look at it coming in, and a lot of the debate about its trajectory and did it make the expected motions or did it not? A lot of that stems from the fact that we just don't have a good constraint on where was it 6 months previously. Yeah. We're going to get a beautiful orbit as it comes in and as it goes out, no matter what it does.
Excellent. Well, I think it's time we had a look at this visitor. Ariel, you with Unistellar, and you can say a little bit more about the network of telescopes you have actually managed to observe it. Can you say what you saw?
Yeah, of course. So Unistellar basically is a network of telescopes across the world, of small telescopes that people use in their backyard. And we utilize that network as this really powerful tool to monitor the sky. So with comets in particular, it's been really nice to every day take a look at a comet, see what it's doing, how bright it is, how fast is it brightening, how slow is it brightening, things like that. And as soon as this was discovered, everybody was very excited, of course, and we wanted to observe it right away. It was challenging, though. So these unistellar scopes, they're small scopes. They're 3 to 4.5 inches in aperture, and that's pretty small. And this is a really faint object right now. So this is pushing our limits, but due to the excitement of our network, we got a lot of observations sent in. And we had a few where we could see it, but not quite measure it. But we had this one really, really nice detection that you see here on the screen now, where you can clearly see that little dot in the middle. This is a stacked image. So all the streaks you see are stars. And this was imaged over 40 minutes. So the stars are streaked because they rotate in the sky. But we track the motion of the comet itself, stack the images on top of that motion, and we can pull out a signal. So we were able to do that. So even at this faint level, we were able to detect it with small telescopes. So we're really excited about that. And it's important to start early so we can start predicting what it's going to do. This comet, so far, it looks like it has a kind of steep brightness increase, steeper than the typical comet. So it's a little bit hard to tell what's going on. It's normal for a comet to increase in brightness this fast if it's new to the solar system. So it has all these volatiles that have never sublimated before, and it's getting warmed up for the first time. It's kind of just throwing it all out there at once. So this is kind of doing that. And we're really curious to see if it's going to keep doing that all the way through perihelion, or if it's going to change. It might change. So this is an example of the kind of predictions we do. Right now, for Unistellar, we have that one detection. So you see one data point, that purple data point. And we have 2 different predictions being shown here. One of them comes from JPL Horizons, which they get their data from the MPC, the Minor Planet Center, and they have a little bit more data than we do right now. So they're able to show that this might be brighter than a typical comet, whereas that blue line shows a typical comet brightness change according to the one data point that we have. And if it was a typical comet, it would only get to 13, 14 magnitudes at perihelion, where that yellow line is. But right now it's looking like it might be brighter than that, but it's hard to say because its shape might change of this figure. So that's why we have to continue monitoring it. It's why it's important to start early.
Yeah.
Yeah.
So a lot of comets that we have in our solar system have done quite a few passes round, and every time a comet, which is a giant dirty snowball, gets close to the sun, it evaporates and you lose stuff. So it could be that what we're observing here, this is the first time this object has started to lose some of its volatiles, and so you could see as something incredibly pristine, primordial in a way, with this comet.
Yeah, it's a very well preserved. It's a great chance for us to look at this primordial material. And normally that's why comets are interesting for us in general. We get to look at what the early solar system was made of. But now we get to look at what other early solar systems are made of, which is very interesting. So it's a cool chance to have.
Yeah. Well, comets would not normally have radio emission.
Yeah, that's sure. And I have to say, I am not a comet. I'm not a comet expert. I did have to go back and study a little bit and to understand what comets might be doing. Assuming that the object is indeed a natural astrophysical source, which is highly the case as we're seeing from hints from optical data, as Ariel and Jimmy have already mentioned. But comets have certain characteristics to them. The first thing is they have grains, like dust grains around the comet, and they have a cometary tail. That halo, as it gets heated up, can emit light, and this is something known as thermal emission. That emitted light has the wavelength of the emitted light is proportional to the size of the grains. Now, it currently at the distance of this particular object, it's still far away enough to do these kind of observations. So, and it's not going anywhere; it's actually approaching us. So the more it approaches us, the better we have, the better chance we have to detect such an emission. The other kind of emission that comets can do as well, or can generate, is spectral line emission, which has to do with excitation of certain molecules also in the halo of the comet. In particular, in the radio, at least, the wavelength where we can detect such spectral lines are some, for a molecule called OH, actually, find radio emission from that, and that will tell us a lot. The composition of the halo is kind of similar to the interstellar medium, assuming that the comet is actually coming from the interstellar medium, and so it's like rather than it's like a lab experiment where you're receiving data from the field rather than you going to the field and studying it. It's just a remarkable remarkable object to study in general, and hopefully we'll have detections in the radio in the coming few weeks.
Great. We're going to just we're going to do a what if scenario. Okay, this object's coming in, is not emitting volatiles, or it may be emitting weird volatiles. You point your ATA at it because, of course, you have to, and then you pick up a sort of a very bizarre narrowband signal coming. What do you do then? Yeah,
that's a good question, and that's a question we always ask. Always detect signals like that, and this is something that I have to make it clear, is that we are swamped with terrestrial signals that look exactly like what we expect from a civilization that has the capability to transmit, right? Because we are transmitting ourselves. And so the first thing we would try to the comet itself. So the first thing we will try and do is just make sure that that signal is not coming from everywhere on the sky, which is the characteristic of an interferer that is human generated or pretty close to the telescope, right? So the first thing we might want to do is just make sure that this hypothetical transmitter, for now, is actually coming from the from the source itself. And if that happened to be, the case, we will pretty much open that up, and we'll say, hey, there's something that it might be interesting, and so we'll try to follow up with other instruments. And this kind of science sort of follow the scientific method. We need to make sure that other our detection, and then after that, I've done my job. We've done our jobs here, and this is
good. Yeah, that's for another conversation.
That's another SETI Live right there.
Yeah, right. Yeah, so we're going to open up to the questions. I'm going to say hi to people who are joining us from around the world. Thank you very much. And I have lost the tab that shows me where people are coaching in from, but thank you very much for everybody. I'm going to turn over to the questions now, and there was one from Raj that I've now lost, so I apologize for not bringing this question up. And that's there was a recent discussion on the age of the comet, and there was a statement that this may well be an incredibly old object from another star system, and one of the arguments for that is where it appears to have come from in the galaxy. Jim, can you say a little bit more about this idea that this is an incredible?
Yeah. Well, I mean, we also are looking at it from a sort of compositional standpoint, and so I think again, as Ariel said, if it's the first time it's passed close to a star, it's going to emit a lot of things. It's going to have a lot of volatile elements they're going to sublimate off. That's also a hint that it's probably very old. But from an orbital standpoint, it seems to be coming in with an orbital trajectory that is, we don't know which star it's from. We don't know exactly where it came from. It's probably been wandering around interstellar space for millions, if not hundreds of millions of years. And it's coming in on an orbit that is consistent with what we call the thick disk, or the so-called old population of stars in the disk of the Milky Way. We think of the Milky Way as being this big sort of pizza-shaped thing, has a sort of ball of stars in the middle, which is the sort of core. But most of us in the Milky Way live kind of in this big disk, this sort of flat plane of the Milky Way. The youngest stars tend to live down in the center of the plane where they're born, where the gas is abundant and there's lots of mixing. And then over time, stars get kind of kicked up and down and sort of perturbed, and our orbits get sort of perturbed up and down. And so the older stars tend to be up sort of out of that plane, sort of raised up a little bit out of the plane. It's just population of stars. And so this thing is coming in on an orbit that looks like it probably originated from the thick disk, but we simply don't know. This is really speculative. What we do know is that it's on a different orbit than the other two interstellar objects that we've seen, which have sort of come in on really steep orbits from above the plane of the solar system. And so it's moving very fast. It's kind of moving with us. And so we won't really know about the population of these objects until we have the Rubin Observatory, which will find dozens to hundreds of these. We can start saying more about the statistics. How often are these rocks launched, and what are they made of, and where might they come from, sort of statistically speaking, demographically?
Yeah. It's interesting, isn't it? We obviously get very, very excited about this object as being only the third, but with the technology, as you say, the Rubin telescope, this is going to become not routine, but the sample size is going to get so large that we will be able to build a very good picture of the interstellar space and the objects moving through interstellar space as a sample.
Current estimates are somewhere between, we'll detect one a month to one a year. Mm-hmm. And that means maybe we'll have 10 of them to talk about after the 10-year mission of Rubin, or we'll have hundreds of them. Right now, we don't know. I have not heard an argument yet this week about if we think that has been constrained now to 2 a month or 2 a year. I don't know if the statistics are in yet. Mm-hmm. I would bet $1 that we're going to have updated statistics in the next few weeks just from this object alone.
Yeah. Thank you. And that's very exciting news for Unistellar. Question from Hannah about the orbit when it eventually passes Earth. How close will it get? Can you say a little bit about the orbit of this object compared to the Earth? And how visible is this going to become to small telescopes? Will people be able to go outside and observe this in some way?
Yeah, I could say a little bit about that. So this comet actually, when it comes to perihelion, it won't ever get very close to Earth. And that's because the Earth is going to be on the other side of the sun when this comet comes close. So it's actually going to get pretty close to Mars. If we were on Mars, that'd be nice for observations, but we're not, we're on Earth. So there's going to be a period of time during perihelion where it will be too close to the sun for us to see at all. So we'll have to wait 5-6 weeks, I believe, is the amount of time where we're not going to be able to observe it at all. And that's when it's going to be at its brightest. But even so, it's never predicted to become naked eye. So we're always going to need telescopes to aid us in seeing this object. So if you have a small telescope from now until through December, barring the time where it's closest and should be the brightest, you should be able to take a look at it.
Yeah, excellent. And that sort of answers a question that Raj put up, whether it will ever be a naked eye object. And the answer is no, not this time, sadly. There's a question from Time Command. Should an object like this hit Venus or Mars, would that be a bad day for us? I don't want to go into cometary impacts and everything like that, but how big is this object? So what are we looking at, Ariel? Size-wise at the moment, what's the estimate?
Yeah. Okay. Size-wise, this has been a big topic lately. Actually, we don't know, and we don't know because the object is fuzzy, right? So it has a coma, and when an object is active, it has a coma. It has all this dust coming off of it, and this is a very dust-heavy comet right now. That reflects a lot of light. So a lot of the brightness that we're seeing is coming from that dust, that coma. And we don't know exactly how much of that brightness is coming from the nucleus itself, the solid part. It's probably not huge. It's probably a kilometer or so in diameter, if I had to guess, like similar to the size of Borisov, perhaps. We don't know, though. We're going to need more observations to figure out where most of that light is coming from. That's going to be better when it comes closer, and we can make those kind of estimates on what that coma looks like. Precovery data is also helping us with that too. The farther away the comet is from the sun, the less active it is because the less it's being heated. So hopefully we can draw some more constraints based on that data. There's some right now, but it's still pretty broad. But it looks like this comet isn't going to be anything giant. And it also right now is not going to hit anything. We have a pretty good grasp on where it's going. It's not going to hit Mars. It's not going to hit us. It's not going to hit anything else. If it did hit something, it would also depend on how it hits it and whatnot. But this object is moving really fast. So it would definitely kick up a lot of debris from Mars. Maybe we'd get a couple good meteorites from it, but it shouldn't be devastating for us.
Yes, as the energy of impact goes as the square of the velocity, for those of you who want a little bit of maths, you don't want things very, very fast hitting you, especially if they're a mile across. I just want to wrap up here because we're almost out of time. We'll start with Jim, actually work through, and then Ariel, and then Wael. This has arrived. It's great. Just starting to observe. Jim, from professional large observatories, what is the process now, and what sort of things will you be looking for? And then we'll turn over to Ariel with the citizen science, and then Wael for the radio.
Yeah, well, I mean, I know that a lot of people are excited about Rubin, and it's had its first look and first light images come out just a couple weeks ago. This object is passing through the commissioning field, and so my understanding is we do have a handful of observations of it. They're not processed and released yet, but it's really exciting for us that in the very first weeks of this 10-year survey, we have the perfect test case just passing right through. Nature has been very kind to us this year. From a professional development standpoint, I think this is going to be a really good test of all of our resources, from follow-up equipment to spectroscopy to everything that we need to understand the composition of this object. So it's going to be all hands on deck with this and anything else that comes flying through in the next couple of months.
Yeah, excellent. And Ariel, the citizen science campaign has only just begun, hasn't it? And maybe say a little bit about how people could get involved and check this out.
Yeah, so our campaign are always posted on the Unistellar website. And so if you have a Unistellar telescope, you can upload your data and I'll analyze it and you'll be part of this campaign. But a lot of people submit their data several ways to several campaigns across the internet, like to the MPC, for example, the Minor Planet Center. There's the COBS database, the Comet Observations database. You can go directly through there if you don't have your own unistellar telescope as well. But yeah, if you do, you could definitely take a part of our campaign, and we're going to be trying to understand how fast this is brightening and what it's going to do in the future. And what we really want to know by this is what it's made of, right? How volatile is this thing really? It's already active at such a far distance. That means it has some pretty crazy volatiles, crazy as in something other than water. But we want to know, how do those volatiles affect what we're going to see? So we got to monitor as much as we can over its whole orbit that we can observe it. That's our goal.
Great. Well, what's the ATA going to do from now? I suppose it depends on what they find, but
yeah. I will say as well, in the radio, we have the advantage that we can actually observe during the day as well. So, unlike optical, you have to make sure that you observe during the night because the sun is super bright. Now, as long as the source doesn't, get too close to the sun, because the sun is also a radio transmitter, we will keep monitoring the source as it gets closer and closer to the sun. The closer it gets to the sun, the more heated it gets, and this is when we have the higher chance of detecting radio emission from it as well. And so the plan over the next few months is to pretty much keep an eye on it, have the ATA monitor it every few days, depending on sort of our observing schedule, and to pretty much throw all of our techniques at it. From trying to detect narrowband transmitters to trying to detect continuum emission or detecting spectral line signatures. So really narrow emission or absorption lines. So all of these are things that we are kind of do for the next few months until the visitor leaves us.
Until it heads back out into interstellar space and continues its journey, which is very romantic, and that's a good way to end our SETI Live. Thank you, everybody, for tuning in to this conversation. I suspect it will not be the last conversation on this object as it continues its journey through our solar system. Thank you very much, Jim, for joining us, Ariel and Wael. Lovely conversation, great questions coming in. Reminder that the SETI Institute is a non-profit research center, and we do rely on donations. So if you enjoyed this and you have some spare change, drop it our way. This will be living on our YouTube channel on the web, so definitely take a look if you missed it, most of it this time. And we will be back with a SETI Live next week. So thank you, everybody. Thank you for joining me and joining us today. Take care.
Thank you.